Hello, my name is Jovan Alega, and welcome to a presentation on the theory, measurement, and guideline limits for rail vibrations on residential buildings. Rail vibration is caused by the unevenness between the two surfaces in contact, such as the wheel and rail. It can be perceived as both an acoustic sensation, also known as sound, and a dynamic sensation, also known as vibration. These vibrations are generally perceived through a building on the ground as gentle shaking or trembling. This is known as ground-borne vibrations. The forms of sound are ground-borne noise, also known as vibration-induced noise, which is defined as noise generated inside a building by ground-borne vibrations generated from the passing of a vehicle on rails. Airborne noise, which is generated by the wheel-to-rail contact, as well as the additional equipment on board the train. For high-speed traffic, aerodynamic noise may also be relevant. The form of vibration is ground-borne vibration, which is generally generated by the interaction between the train, the track, and the subsoil. The vibration is transmitted through the ground and may reach the foundation of a building. Vibration strength is usually measured as RMS, or root mean squared vibration velocity, in millimeters per second. Light rail trains, also known as streetcars, have an RMS vibrational velocity of around 0.06 millimeters per second. Commuter rails, shown here, have around 0.17 to 0.53 millimeters per second. High-speed rail trains, about 0.25 millimeters per second. And underground rail trains, also known as subways, around 0.25 to 0.5 millimeters per second. These velocity levels can be converted to a logarithmic scale, as described later in the presentation. Rail vibrations always influence the surrounding buildings and environments, but their impact is dependent on the strength of the signal and the type of train. The foundation is also an important factor, as some buildings may react in such a way that the vibration is transferred through the structure. Minor cosmetic damage, such as small cracks in the foundation or walls of a building, may occur. In cases where minor cosmetic damage does occur, there are often many more credible causes, such as natural aging of building materials, moisture, weather, or temperature variations. There's many other factors that can cause these cracks. Calculations and simulations must be conducted when developing a new system to ensure that the negative effects of rail vibrations are mitigated. In order to develop these models, data must be obtained to determine the water content, density, and shear wave velocity. Some of this data is obtained directly from soil samples, but vibrations in the earth can also be measured using an array of geophones. A geophone is a device that converts motion to voltage. This is accomplished either by using a coil mounted to a spring that moves relative to a magnet, or by a mass elastically suspended with small air gaps on either side acting as variable capacitors. For the study of rail vibrations, geophones are generally configured in 3-component arrays. This means that each array actually has 3 geophones to measure motion in each dimension. All the arrangements shown are using 3-component geophones. They are simply spaced several meters apart and are often placed at ground level. Sometimes, however, they must be placed below ground in a similar vertical distribution. The data is collected from the geophones is usually sent to a data acquisition instrument, which can convert the raw output of the sensors into usable information. It is sent to a PC that can pre-process the data using software such as MATLAB. After being compiled and graphed, it can then be compared to acceptable levels when developing a new project, or the data can be used to help conduct analysis on other projects. These projects must follow government laws and regulations that protect both new and old buildings. An effective way of knowing whether the rail system will cause damage to surrounding buildings is to calculate the vibration velocity caused by moving trains in relation to the distance between the rail and the building. Vibration velocity is calculated as shown. Damage starts to occur when velocity levels exceed 85 vibrational decibels. According to the United States Department of Transportation and the Federal Transmit Administration, if ground-borne vibrational velocities exceed 85 to 100 vibration decibels, damage to surrounding structures are likely to occur. However, it's unlikely that a transit system will exceed 85 vibrational decibels unless it's operating at an extreme speed or with uneven rail surfaces. Therefore, if a train is operating at normal speeds with smooth rail-to-wheel contact, it's likely to operate within its restricted guidelines. Most commuting rails operate below 85 vibrational decibels, thus are no risk to buildings that are further than 50 feet. When rail vibrations exceed a certain limit, mitigation measures need to be taken into account to reduce the vibrations. Measures can be implemented on railways, trains, residential buildings, and the land between the railway and residential building. Vibrational effects can be reduced by constructing railways on soil that is stiff. Vibrations are reduced for soils with a high dynamic elastic modulus and shear wave velocity. For existing railways, the stiffness of the soil can be improved by mixing binder into the soil. And another method of reducing vibration is to use continuously welded rails instead of jointed rails. Trains equipped with secondary suspension systems also have lower levels of vibration, and secondary suspension systems and wheels must be regularly maintained to ensure minimal vibrations. Mitigation measures are easiest applied to on residential buildings when they are designed and constructed. The most effective way to reduce vibrations on residential buildings is by applying an elastometric bearing in the foundation. The most common barriers used are water barriers, concrete walls, or steel walls. The concrete and steel walls are much more effective at reducing vibrations because they have a higher stiffness than water, but those methods are far more expensive. Thank you for listening to our presentation, and if you have any questions, we'd be happy to answer them. Here are our references.